Hello and welcome to this course. I'm Dr. Sriram Kumar. Today we are going to learn chemical methods of nanomaterial synthesis. In last class, we had discussion about the nanomaterial synthesis using two different kind of mechanism. One is top-down approach and the second is bottom-up approach. And we had discussion about the physical methods of nanomaterial synthesis. For example, we studied about those mechanical screenings, ball milling technique. We have discussion about PVD and CVD technique and sputtering technique in the physical method of nanomaterial synthesis. We also learn biological methods of nanomaterial synthesis. So we understand the biological entities, bacteria, enzymes, and algae or yeast, how that biological sample of the system can synthesize the nanomaterials. And then further, we study the use of the plant and the extract for nanomaterial synthesis. Now we are going to learn about chemical methods of nanomaterial synthesis. So in this topic, we will learn key important kind of the techniques. For example, as we will learn about scope specifications method, we are also going to learn about chemical reduction of metal salts, electrochemical method. So I will make the separate video on electrochemical methods because this is widely used technique. And we are also going to learn about the microemulsion method, sonochemical method, and the Solzil process. We are not going to use the pyrolysis or maybe the phytochemical method. So here we are going to learn one, two, three, four, five, six different chemical methods technique for nanomaterial synthesis. Okay, so when we think about chemical methods nanomaterial synthesis, so we have two methods. One is the reduction method, and the second is the sedimentation method. So in the chemical reduction method, we can use maybe the polyol, maybe the organic acid, maybe sodium borohydride, and the sugar for the chemical reduction process. And maybe we can use the indirect reduction using photo reduction mechanism, or maybe the gamma hydrolysis, ultrasonic wave, and the microwave technique. And in the sedimentation method, we have the sol gel, very important method. We have the hydrothermal technique. So these are the widely used methods, sol gel and the hydrothermal techniques. So we will have understanding about this kind of techniques for nanomaterial synthesis. So when we think about chemical methods of nanomaterial synthesis, so for that, first we have the precursor here. So we use precursor and we dissolve that precursor in solvent, and we have that precursor in the solution phase. So that precursor, so we have either the liquid phase, maybe the solid liquid phase kind of the interface. And there is kind of those intermediate process happens, and that leads to the nucleation for the nanomaterial synthesis or nanomaterial growth. And once the nucleation process happens, and so that is kind of this primary particle. So this primary particle we can say is the nucleus or maybe nuclei. And once there is kind nucleation process started, there is kind of the further process, either is the growth process happens or maybe the agglomeration process happens, and based on we will have the maybe we have nanoparticles, or maybe we will have nanoclusters. So it depends on the mechanism, either growth mechanism, maybe the agglomeration method, and we have nanoparticles or nanoclusters. So in this technique, we have two important parameters if you think about the nanomaterial synthesis. So in nanomaterial synthesis, so let's understand the nanomaterial synthesis. nanomaterial synthesis. So we have two key important parameters. One is the nucleation process and one is growth process. Growth process. So now let's understand nucleation process and the growth process in details. So in this class, we will learn about the thermodynamics and kinetics of the nucleation process and the growth process. So here, the nucleation process is kind of the first phase, that there is new kind of the thermodynamic phase that forms for in the process of the nanomaterial synthesis. So here we have here, suppose if I explain, we have the metal salt in liquid phase. We have liquid phase, right? In the liquid phase, we have metal salt and there. And so what happens? So that reduced and we get M0, that means that is the in atom. And in atom forms, so what happens? So there is first is kind of the atom forms and further there is nucleus or may be nuclei and that nuclei further grow into the kind of the nanomaterials. So these are the steps in the nanomaterial synthesis. So here this is in the liquid phase, however this one is in the kind of the solid phase, right? So that's why the nucleation process is the first process that starts with the new thermodynamic phase from the liquid phase to the solid phase. So here we have the here's atom or molecule, molecule that depends on the kind of the system we use, and this one they can nucleation process and the nanomaterial synthesis. So here, if we need to understand this process, that is the nuclei or the nucleation formation, so nucleation formation. Okay, so here we can also say the nucleation process is kind of, we can also say this kind of the solidification process, because we are getting solid phase from the liquid phase, right? So let's understand how the nucleus process affects the nanomaterial synthesis. So based on the number of the nucleation in the system, so that will affect that determines the number of the nanoparticles. Maybe it determines the size of nanoparticles and the location of the nanoparticle in the system. So it is very important to understand what is the size of the nucleation process of the nuclei. So here, so that nucleation affects the properties of the nanomaterials. It is important to understand how that nucleation process affects the nanoparticle size and the locations. And this is all about the thermodynamics and kinetics process. So if we think about the nucleation process, so we have normally two kind of nucleation process. One nucleation process is the kind of the homogeneous nucleation process. And the second is kind of the heterogeneous nucleation process. So in homogeneous nucleation process, so suppose we have one beaker and we have the solution. We have the solution there, right? So in the beaker, if we have the solution, and suppose we have Mn and then it will form M0. Suppose there is the atom there and there is some kind of the agglomeration process happens here. So there is the growth of the embryos and then further there is nanomaterial. So what happens in the homogeneous nucleation process, you have the same phase, right? So this nucleation process starts when if there is no such kind of the foreign particles or the foreign surface. So that nucleation process starts within the system at the solution phase. However, in the heterogeneous nucleation, we should have such kind of external on a foreign surface. But that foreign surface may be the kind of this container of the wall of wall container. Maybe we have the impurities, maybe defects. So these materials can act as the foreign materials, and based on that foreign materials, there is the growth happens on that maybe defect impurities of the containing wall. So based on the growth of the nucleation, we have the energy difference between homogeneous and heterogeneous nucleation. And for the homogeneous nucleation, we have always higher energy barrier as compared to the heterogeneous nucleation. So if you want to understand So if you want to understand what is process here, so this is the homogeneous nucleation. And the second, if we have kind of things here. So if you want to understand from here, so here we have the higher energy barrier as compared to this one. So what happens? There is always higher barrier for the homogeneous nucleation as compared to the heterogeneous nucleation. That is the energy difference from the liquid to the solid form. And because of that energy barrier, the new homogeneous process, nucleation process is slower as slower. That is the slower process as compared to the heterogeneous nucleation. So we understand if nucleation process starts, so they are the kind of the process. So there's kinetics and thermodynamics systems comes to play an important role. First important thing is that for the homogeneous nucleation, there is kind of the higher energy barrier, and because of that, so you will get the slower process. And for the heterogeneous nucleation, that process needs lower energy as compared to the homogeneous process, and that's why you get. So this process is the faster process. So this is about the difference in the nucleation process. So now let's understand what is the nucleation process. So till now we understand that we have metal ion in solution phase, and that metal ion that is reduced to and that forms M0. So this one is in the liquid form, right? And what happens if we have the metal, and that metal, the metals combines together and that forms kind of the smaller particle, and that smaller particle is called embryos. So first step from the metal to form the solid particle, that is called the embryos, and from that embryos we will have the further bigger size, and that bigger size of the particle is called here the nucleus. Nucleus, or maybe we can say here the nuclei. So we need to understand here. So here embryos has always a smaller size as compared to the nucleus. And in other way, we can say here is if the embryos has the critical size. So in this case, if we have the R star there, and if you have the R here, so here, if that the size of the embryos becomes the critical size, so that becomes the nucleus. And further, from the nucleus, there is the growth process happens, and we get the nanomaterials. From here, we get here the growth process, right? And this is called end of the nucleation process. So we need to understand this nucleation process and this growth process. So what happens here, we have the small ions, and that's because of the small ions, maybe we have the size is 0 to 3 nanometer, or maybe the smaller than that. And there is the kind of condensation process happens, and there is the formation of the embryos. So once we get the critical size of the embryos, so that is called the nucleus, and there is further condensation process and happens, or maybe the coagulation process happen, and there is the further growth of the nanomaterials, and ultimately we will get nanomaterials. So these are the steps in the nucleation and the growth process of the nanomaterials. So now let's understand what are the key factors that can affect the nucleation process. So one important is the supersaturation process. Supersaturation. So here the supersaturation is about the concentration of the nuclei particles here. The second is the temperature, and third is solvent properties and the capping agent. So these are the very important parameters that can affect nucleation process. So we are going to learn in details about each step, each factors, how these factors affect nucleation process. So first, let's start with supersaturation concentration. Suppose, so here now we are going to learn the effect of supersaturation concentration here. So if you want to monitor concentration of that nuclei particle here with the time. So at initial stage, what happens? We have this process happens, right? There is a kind of, if we take the example of a detection process, then we will have the detection of the metal ants here. So what happens? So in the first stage, so there is the increase of this concentration. So up to this time that it needed to increase the concentration to up to here. And once that it is in the second phase, with the maximum range. So this concentration, so the range, the concentration in this particular time period is required for nucleation process. That means that much concentration we need to start nucleation process. And once we have the nucleus, so first there is formation of embryos there, in embryos, and then after we have the, now we have the nucleation process. And nucleation, so we have nuclei here. So we have nucleus, right? So we have nucleus now. So once we have the nucleus here at this stage, at this particular concentration, and this time at this particular time here, what happens? Then after we will get kind of growth phase, right? So growth phase we have this particle there, M0, M0, M0 kind of things. So that will come together maybe in the process of the coagulation process, maybe the condensation process, and then for the growth, so growth happening there. So here, so that particle from bulk to that interface comes by the diffusion process. Diffusion process. So because of that diffusion process from the bulk to the interface on that nuclei, there is a growth process happens. And because of that growth process, we have the here, the exponential decrease in the concentration with the time t. And finally, we get here nanomaterial. So finally, we get the nanomaterial here. So this nanomaterial has the bigger size, and that has the many particle there. So we get in the nanomaterials, right? So this shadow part is the growth phase. So here, so we can say is the once we get the nucleation process, so there is the further growth process, and we get the nanomaterials. And once the nanomaterial forms, so there is kind of the equilibrium concentration of that, and there's a bulk concentration, and we get the concentration. There's bulk and in the particles. So here, this is the kind of equilibrium concentrations happens. And this is about the nanomaterial synthesis or nucleation process and growth process. So now let's understand the other things, and that is a very important point is that, so we will have different kinds of the nucleation process and growth process. So first case, if you have, the first example is A. The condition is A. So in condition A, once we get this much concentration in this particular time. So this is for nucleation process. Nucleation process. So once we get the nucleation process, what happens? So this phase is for growth phase, right? So this is for growth phase. Growth phase. So once we get the nivelations for A, so there is a sharp decrease in the exponential decrease in the concentration because of the diffusion of particles or atoms from the bulk to that surface, and that's why there is this exponential decrease in the concentration, and it's called the growth phase. And then after we have the equilibrium concentrations happen. So here in the condition A, there is fast, because that nucleation process has very limited time from here to there. So this process has fast nucleation process, nucleation process, and growth process both. So in first case, there is the fast nucleation process, and the second is the growth process, and that is kind of the diagram. It's called the Lamar diagram. And the second kind of the growth is for the B. So in the first kind of the growth, we will get a small particle size. So in this first case, in the case if you have the fast nucleation process, nuclear process, what happens? Ultimately, we will get a smaller particle size. This is the beauty of the first case. So what about in the second case? We have second case where we have there's an integration process happens, but then after, so because of this one, this is kind of the agglomerations happens. So this third is the case about, so third is the case that is C for the Ostwald's ripening process, Ostwald ripening process. The third is the Ostwald deepening process. In the Ostwald deepening process, what is happening there? Let's understand this one. So in the second case, third case, we have this much. If it is thing about the time, so let's understand this time for. So this is in the third case, in the Ostwald deepening process, we have this much time is required. So here they that nucleation process needs very longer time. If the nucleation process has very longer time for nucleation. So if we have the longer time for nucleation process, what happens? So in that case, first you have a smaller particle, and then after you get the kind of the smaller particle and the bigger particle. So that bigger particle is formed based on the expense of the smaller particle, because there are many small particles combined together, and that forms the bigger particle. And then after there is further increase in the size of the nanomaterial. So in Ostwald deepening process, we will get here the bigger nanoparticles. So in this case, we will get bigger nanoparticles as compared to condition A. So in condition A, we have fast nucleation process and a growth process. However, in type 2C, we have Ostwald deepening process, and in this we will get bigger nanoparticles. So that are the difference if we are controlling the nucleation process. And so once again, if you want to understand what is the thermodynamics of the nucleation process, we need to understand this key point here. So till now we understand we have three different kind of the things here. So let's understand the nucleation process. And that nucleation process starts. So we understand that if we have and there is reduction process happens, so we get the atom, and from that atom we get embryo, embryos, and from embryos we get the nucleation process of nucleus, we get nucleus or nuclei, right? So what happens here is the embryos and the nucleus. So nucleus is the critical size of embryos, and once we get the critical size of nucleus, then we will have the growth phase and we get the nanomaterial, nanomaterials, right? So here, so that embryo, so let's understand the nuclei has critical size, that is the R star, and the size of that embryo, that is the first solid particle formation. So this is in liquid phase, and this is in the solid, right? So what happens is solid, there is a formation of the new thermodynamic phase from the liquid phase, and this process maybe we can call it a solidification. So we have process happen, that is the solidification process. We have liquid, and that liquid is converting into the solid form. So we need to understand what is this change in the energy from liquid state into the solid state, right? So here, so that embryos is the smaller size of the solid material as compared to the nuclei. So nuclei is the critical size. So suppose we have liquid and we have solid. So from, if you want to make the solid material from the liquid, we should have the critical size of that embryos. Otherwise, what happens? So that solid gets dissolved into the liquid form. So get dissolved. So if you want to prevent that dissolution, if you want to prevent that dissolution, we need to have that critical size of the embryos so that there is further development of this nuclei. So if we have this liquid and the solid form, we need to understand the energy difference between the liquid and the solid, right? So if you want to monitor the change in Gibbs free energy and temperature, so we will have the kind of this system here. So here, let's understand these parameters. So this parameter is for the liquid and this curve is for the solid material. And that intersection point is called Tm, that is the melting temperature. So if you want to monitor change in the Gibbs free energy below the melting temperature and above the melting temperature, we will have the change in the energy here. So from this plot, we have the, if the, so first case and the first condition is about if temperature is less than Tm. That means we are talking about below melting point temperature. So it is below melting point temperature. So if you want to develop solid materials, we should have the working temperature of the solution. A system should always less than the melting point of the solidification process, right? So if this temperature is less than the melting point temperature, what happens? In this case, we will have Gibbs free energy for the solid material, solid phase is less than change in the gas free energy for the liquid state, right? So in this case, we will have change in delta Z is equal to del Gs minus del Gl is equal to negative. So here what happens, mm, so in this particular range, we have delta Z is equal to negative, and that is for the solidification process or maybe for the nucleation process from the liquid to the solid phase. And the second things is about here, if this temperature is greater than Ta, so in this case del Gs is greater than del Gl, and in this case we will have delta Z is equal to positive. So we can say here, so in this particular case we will get delta Z is equal to positive. So in this case, we have delta Z is negative below melting point temperature, and above melting point temperature, we have delta Z is positive, right? So this is about the solidification process from solid to the liquid. So if you want to develop nanomaterial, we need to have that temperature should be below the melting point temperature. That means delta Z for the solidification process is zero, is negative. And that's why here, if you want to understand this curve, so this curve, so this is about the delta Z for the solid material formation, and we can say is the delta ZV, because there is a solidification process happens. So here the volume, let me write again. So from liquid to the solid, there is formation, and based on that, there's kind of the volume growth, right? And because of that volume growth, we have here delta G, and that is negative. And from that volume contribution, we have negative values. However, we have the second kind of the parameter is that surface energy. So if we have solid material from the liquid, what happens? We have the different kind of the energy change, and that is about the surface energy change. So let me write, we have those two key parameters, and that key parameters is the solid material. So we have those two parameters, and that is, one is surface energy, and the second is the Gibbs free energy. Gibbs free energy. So these are the key parameters, and that affect overall the growth of the nucleation process. So here the surface energy has, so this surface energy is positive, and this is zero, and this is negative. So volume contribution is negative, surface energy is kind of the positive contribution. And if you want to understand overall the energy, thermodynamic energy in the nucleation process, we need to add up the overall the energy level, right? So now let's understand. So we have these two parameters. One is for the Gibbs free energy. So let us consider delta GV is Gibbs free energy per unit volume. So here gives free energy per unit volume between liquid and solid. And delta, maybe I should write here gamma, that is the surface energy. Surface energy per unit area between liquid and solid. So we have the volume contribution, and we have here surface energy contribution. So let me write the overall total energy. So we have here total energy is, we have contribution from the surface energy, we have the volume energy. From volume and plus surface energy, right? Surface energy. So we have from the volume energy and the surface energy. So we can write here is, so this is for the per unit volume. And if we just consider the spherical particle, what happens? We have 4 by 3 pi r cube, and we have delta GV. And for the surface energy, we have 4 pi r square, and we have gamma. So this is about total energy, right? So this is total energy that is a contribution from the volume and the surface energy. So if you want to understand the critical size of this embryos in the case of the nucleus, so if you just combine two parameters, and both parameters are competing to each other, so in this case, if we just combine together, we will get into this kind of the maximum point. We will get this kind of the maximum, this kind of the curve. And we need to know what are the critical size. So at particular size, we need to understand what are the radius or the critical size of embryos. So here, if you want to know, so pick maximum values. So for that, we need to, so if you want to, so here we want to know what is, here question is, what is critical size of embryos? That is R star, or maybe RC, or maybe I should write here is the uh, maybe RC. So that is the critical size. So if you want to know what is the critical size of the embryos, so what we can do, we can just differentiate del GR upon dr and make that is the 0, and that is, so this is the conditions. So if you just put this condition there, then we will get the maximum R values here. So let me write. So here in this particular equation, we have this R values, and this R is, let me write, this R is the radius of embryos, right? So let me find out the critical size of R here, and that is all about. So what happens here is, if you just use this one, R by dr is equal to 4 by 3 pi 3r square del GV plus 4 pi 2r and gamma, and that is equal to 0, right? So we have here is, if this cancel out these three to these three, so we have here 4 pi r square delta GV is equal to minus, so it is 8 pi r, right? So this is 2, we have this RCA, this is cancelled out, and and here this R is kind of the static R is equal to minus 2 now by delta GB. So this is kind of the critical size. So this is critical size of, this is the radius of nuclei, and that and So from this equation, we get here what is these are values. So here, this R value is equal to minus 2 by del GV. So this much radius of the nuclei is needed for the growth of the nanomaterials. So now we understand this radius, and if we just put this value here to find out what is the total, and from this one we need to find out what is the critical size, a critical delta G values. So if we just put values here, we will get 16 by 3. I will get by gamma 3 upon del G V to the power 2. So this much amount of energy is that is the delta Z values. So this is the delta Z values here. And from this one, we will know, okay, this much gives free energy is there for the nucleation process. Or maybe we can say is that this is the energy barrier for the growth of, there is the nucleation process. So that is the needed in the terms of the thermodynamics to understand what is the energy barrier and how that energy barriers will affect the nucleation process here. So once we understand that energy barrier, then we can understand the different parameters. So in tomorrow class, we will understand the effects of temperature on the nucleation and the growth of this particle. And then we understand the other important factor, that is the effect of the viscosity, maybe the concentration or the energy barrier on the process happens. And we further understand the difference between the homogeneous and heterogeneous nucleation, and how we can explain the difference between this energy barrier in the next class. And then after, we will have the understanding of the growth phase of the nanomaterials in terms of we have the two kind of the mechanism. One is a diffusion control mechanism, one is surface process mechanism. And for the growth of nanomaterials, we need to understand which step is more predominant in the terms of the nanomaterial synthesis. So see you in the next class, in which we will have important discussion about the factors affecting nucleation and the growth stage of nanomaterials. So see you in the next class.